Okay, in this show me, we're going to attempt to do numbers 1 through 4. So on the non-multiple choice section. So number 1 says a little girl is on a playground swing and she rises to a maximum height of 2 meters above the lowest point on her swing. So here we have her swing, and it is 2 meters above the lowest point that she reaches. So if this is the lowest point, okay, that's the lowest point on the swing. She's 2 meters above it, which means that up here she has gravitational potential energy, and down here she has kinetic energy. The kinetic energy is connected to that velocity there, and it says that she's just pulled back and let go, right? Or that's what we can assume, because it doesn't say she got pushed back. It says the swing rises up to that height, so we can assume that the kinetic energy at this point is equal to 0 because there's nothing going on there. It just says it rises at that point. And then we can assume the gravitational potential energy at this point is also equal to 0 because it's the lowest point on the swing. So what that tells us is that gravitational potential energy initially equals the kinetic energy finally. So now we're going to plug in numbers. mgh equal, or not numbers, but rather symbols. mgh equals 1/2 mv squared. And you may go, oh, we don't know the mass of the girl. Well, that's very convenient because we can cancel out the m's. Alright, so we're left with gh, so 10 times 2 equals 1/2 times v squared. And so now we have 20 equals 0.5 v squared. Then we have 40 equals v squared, square root, and we get the answer is 6.3 meters per second. And that's equal to the velocity. Okay? Number 2. Same deal, except this time, instead of the girl being on a swing, she's on a slide. Okay, and up here at the top of the slide, our girl has gravitational potential energy. Down here at the bottom of the slide, she has kinetic energy and no gravitational potential energy because she's used it all up. And she has no kinetic energy up here because she hasn't started moving yet. In the course of sliding, she loses 100 joules to heat. Okay? So what this means is the gravitational potential energy initial should be greater than the kinetic energy final because she lost 100 joules. So when we plug in our formula, gravitational potential energy initial equals kinetic energy final, like we had here, we have to, like this right here, we have to change this a little bit to add in that energy loss due to heat. So we have to add in the heat lost, HL. Alright, so let's figure out what the gravitational potential energy of this girl is, right? It's 20 times 10 times 2, and that should equal 1/2 times 20 times, v squared, and then that should be added, we can add in 100 joules there. Okay, so if we go here, we should have 400 joules equals 10 v squared plus 100. Subtract 100, we should get 300 equals 10 v squared. 30 equals v squared. And we should end up getting 5.47 meters per second is equal to the velocity of our girl. Now you'll notice, despite the fact that they went from the same point, both of them were at 2 meters up, this girl went slower than this girl. And that's because this girl in this problem had 100 joules of heat lost. Okay? So that's number 2. Alright, number 3. Number 3 is a 200 gram marble, so it has a mass of 0.2 kilograms. Is projected straight up from an elastic or from a spring loaded launching device that stores 100 joules of elastic potential energy. Okay? And then it asks, how fast was the marble going when it leaves the spring, and how high does the marble go? Well, we have to know two things, all right? Or actually three things. Number one, this is the initial position. Right here. We have the initial setup. If this is the spring, all right, it's compressed some distance x, all right, and the little, whatever, is it a ball? No, it's a marble. But we'll just call it square because that's what I drew. All right. And then afterwards, it's up here. It's used up all of its potential energy here, and the block now, or the marble now, has a velocity upwards. And then the spring really doesn't have any play anymore, but now it's up here some height, h. Alright? Obviously, here it's got elastic potential energy. Here it's got kinetic energy. And here it's got gravitational potential energy. Now, since energy is conserved, and it doesn't mention anything in the problem about losing energy, we can assume these three things are equal, which means that the kinetic energy at this point should equal 1,000 joules. And the gravitational potential energy at, we'll just call this point 1, point 2, and point 3. And so the kinetic energy at point 2 should be 1,000 joules, and the gravitational potential energy at point 3 should be 1,000 joules, because all the kinetic energy should be lost here. There should be no potential energy and no elastic potential energy there, and there should be no kinetic energy or gravitational potential energy there. So they should all be equal. Alright, so what that means is that 1/2 times 0.2 times v squared equals 1,000 joules. So that means that 0.1 v squared equals 1,000 joules, which means that v squared equals 10,000. And then square root, and v is equal to 100 meters per second. So that's the first one. That's from here. For the second one, right here, all right, mgh equals 1,000 joules. So we get 0.2 times 10 times h equals 1,000 joules. So we get 2h equals 1,000 joules, and then divide by 2, and we get 500 meters is the height. So that was number 3. Key thing to remember here is that energy initial equals energy final. The last one is just saying if it's a 50 watt rating, that means that you have 50 joules per 1 second. And that means that if you were talking about, like if you had to explain what 50 watt means, it means you're putting out 50 joules of energy, or it's doing 50 joules of work every 1 second. Okay? That's all it means. Alright? There you go. Questions 1 through 4 on the energy study.